Hey there, in this video I want to talk about one more trick that's used when solving simultaneous linear equations. And that's something called LU decomposition. And so the point here is we want to make Gaussian elimination more efficient. So we're going to have some matrix that we're trying to solve that holds the coefficients in our linear equation. And generically, let's say that those coefficients are A00, A01, A02, A10, A11, A12, and then finally A20, A21, A22. The Gaussian elimination runs us through 3 steps. And those steps, let's call those each L. So we'll do zero index like a good programmer. So the first thing we do would be L0. That would be where we divide the first row by A00, and then we subtract multiples of the first row from the second and third. And then we do the same thing with L1, L2. And so that gives us sort of our Gaussian elimination version of the left-hand side of our equation. And we have to do the same thing to the right-hand side of the equation. So we start with L0, then L1, then L2, applying all those to V, which holds the coefficients from the right-hand side of the equation. And then, just for example, let's look at what these matrices L look like. So the first step, we do 2 things. So we're going to represent that as 2 different matrices. Each will accomplish the 2 parts we want. Remember, when you multiply matrices, it's just like right to left. So we'll start here on the right. The first thing we do is we divide by A00. We don't do anything to the second row, and we don't do anything to the third row. So this is just divide first row by A00. And then we subtract multiples. So we don't do anything to the first row. And I subtract A10 from the second row. I want the second row itself. I don't care about the third row in this operation. And then we subtract A20. Don't do anything with the second row. Subtract the third row. So what this matrix here does is it subtracts multiples. And so together, those are the 2 operations that make up the first step of Gaussian elimination. But hey, couldn't we just multiply out those 2 generic matrices and get a simpler single transformation matrix? The answer is sure. So we could pull out a factor of 1 on A00, and we're going to end up with 100, negative A10, A00, 0, and then negative A20, 0, A00. So that's just the matrix multiplication of what we had on the left. And then likewise, we can find L1 and L2, simplifying them as we go. So already we've kind of doubled our efficiency here by pre-computing these matrices here. Okay, so that's where we are so far. We found L0 through L2. But we can actually do even better than that. So since we have L2, L1, L0, AX equal to L2, L1, L0, V, we could do a little bit of algebra on this. We can take these matrices here on the right and move them over to the left by multiplying by the inverses. Remember, when you do that, you reverse the order of the multiplications. So we'll have L0 inverse actually first, and we'll have L1 inverse, L2 inverse. This is just linear algebra stuff here. L2, L1, L0, multiply AX, all that equals V. Now, as it happens, like the really kind of cool thing about all this is when we work it out, we're going to discover that multiplying all these inverses of L, let's just call that matrix L, let's define it as L, it's what we would call a lower triangular matrix. So because of the steps in Gaussian elimination, it happens that we get a lower triangular matrix. So it's the top right of the matrix is 0, and the bottom left is where you have all the coefficients. And it also happens that all these L's up to and including the A, let's call that U, is an upper triangular matrix. And the nice thing about upper and lower triangular matrices is they are really easy to work with. I mean, the whole point of Gaussian elimination was to make a triangular matrix. So we have now simplified version LUX equal to, that should be a V, LUX is equal to V. And L looks something like this. So we have a coefficient L00, some zeros, L10, L11, some zeros, L20, L21, L22. And you have to go through kind of a long process of algebra to solve for what each of these L's are. It's going to be some mix of the coefficients A that we had in the original matrix, but it's always the same mix. And then we can do a similar sort of thing for U. U is a little bit nicer because it has ones along the diagonal. There's actually only 3 values in here that aren't 0 or 1. 1, 2. And let me fix the alignment here a little bit. So you got to solve for the L, the lowercase l's, and the lowercase u's. But you only do it once. And then, the really handy part of all of this is the solving is now actually really easy. So let's make a new definition here. Let's call u times x equal to y. Basically, I'm just picking out this part right here and calling it y. And then that lets us exploit the fact that L is a triangular matrix. So L times y is equal to v, and that's easy. So you can very easily, very quickly, you're just basically reading across the rows, solve for y. And then once you know y, come back to the original definition, u times x equals y. And u is a triangular matrix, and you've already found what y was, so you just read across the rows, and now it's easy, and you have solved for x, you're done. So once you've done the hard part, and the hard part is finding these things, but you only do that once, so you figure out once on a piece of paper, you program it into your computer, now you can very, very quickly solve your equation. And so that's what is actually used in the equation solver, is linalg.solve, that we'll see in just a moment, is it uses this LU decomposition, pre-computed, and it uses partial pivoting to make sure things are in the right order so you don't have any divisions by 0, and that's what lets you solve simultaneous equations, very quickly considering what you're doing. So now that we have a good idea of how all the pieces fit together, let's look at how we can use the built-in Python function for doing this. We want to, first of all, import linear algebra, and that lives in the scipy package. Actually, you can find linear algebra in both NumPy and scipy, but the scipy version is both faster and in most cases has more features. So we're going to do this as a from. So from scipy, we're going to import linear algebra linalg. Okay, and that'll give us access to a whole bunch of linear algebra stuff. The tab completion still thinking about. There we go. We got all this stuff, and for our purposes, we want to solve here. The most general one is just solve. The other ones are special cases that are faster for their special case. So let's start by making something to solve. Let's go with the same example that we had to write down with partial pivoting, like where you had to pivot it, to show that this method worked with partial pivoting. It does it built in. So A here is going to be represented as a NumPy array. And we'll just do a literal array for this case. So we'll do 0, 1, 2. And I'm putting these decimal places in here because these are floating point values. Solve is actually smart enough that it will convert things up to floating points for us, but it's always a good idea just to not rely on that. So 2, 2, and 1. Okay, so that's the array for A, and then V here was a column vector equal to 1, 0, and 2. And in fact, I kind of like to type it out so it actually looks like a column vector to sort of remind myself of what I'm doing, but you don't really have to do that. Just using some extra white space. And then we're going to get our answers, x, y, z, or whatever variables you want to call them, coming out of linear algebra.solve. If we look at this, it wants A and B are going to be our matrices A and V in our case. And we don't usually have to use these optional arguments here. So we're just going to give it A, we're going to give it V, and let it give us the values, and then we can print X, Y, and Z to see what we get. So x here was -3, y was 5, and z was -2. And that's the same thing we'd get if we worked out this problem by hand. But the nice thing here is that it's going to work for any size matrix. I mean, you're not limited to 3 by 3. You can do 100 by 100. I mean, at some point, your computer will run out of memory if you make the matrices too large. But in principle, you could use it for any number of equations with any number of unknowns.